Little lost. So we can always look back to this recording, which will help, and then I'll make some modified instructions as well. But what I want you to do is I want you to write about learning about general relativity. And because what's happening in this process is you have lived and used your senses to perceive your world. And what I'm really interested in what I want to hear about is how learning about general relativity, what that experience is like and how it makes you question your world, or the frustrations, the parts that are confusing. Maybe look at those, try talking to someone about it, seeing if it makes sense. What are you surprised that you do understand and don't understand after you talk to someone about it? You know what I mean? Because some of this stuff might seem hard, but as you explain it to someone, you might start to get it, and then realize that someone's looking at you like, oh, well, this is all crazy and none of this is true. And you're like, well, actually, wait a minute, it is. And I want to go over if I can find the pen. I found the pen. I want to go over the experiment again, the general relativity experiment that proves that general relativity and not Newton is correct. And it's very elegant because it actually gets rid of all of the, lets you eliminate Newton pretty convincingly. So let's see here. The idea here is that we'll have two things to look at. We'll have a space-time graph. Right, where this is CT and this is X. And we'll have a building. All right. So what we saw is that, looking at Newtonian dynamics in terms of space-time, you could tell yourself, well, the space-time might just be a different way of looking at our dynamic universe, which it is. And when we look at our dynamic sort of 3D space, we get this flat space-time. And so by using light in this experiment, by using these pulses don't have mass. So we can eliminate the gravity field, and since they're going along the same path, even if they did have mass, gravity would have to affect them the same. So if we look at a pulse here, the experiment basically goes like this, and I'll change colors to purple. So if we fire pulses 5 seconds apart, right? So the idea is you have a button, you push it, and you have a clock, right? You set it up to the button so that at exactly 5 seconds later, another pulse is given. So you have delta T1. On the space-time diagram, the location for the top of the building is given like so. And at time 1, you have one sort of space-time event. The photon goes to the top of the building. All right? And then at some later time, at 5 seconds later, you have a photon go up. This is delta T1, and this is delta T2. All right? Now, your logic should tell you, I hope it tells you, that if you let go 5 seconds, if you push the button and fire photons 5 seconds apart, up here at the detector, you would expect that delta T2 would also equal 5 seconds. That's what your intuition tells you, and that's what a flat space-time tells you. So if these two time differences are equal, then Newton is right. And while space-time would be an interesting tool, we could be very confident that Newton's interpretation is right and gravity is a real force, and the stuff we know, or gravity is a physical force. That's what I mean by real. Now, the more scary proposition, if delta T1 does not equal delta T2, then these lines are no longer parallel, right? That means that eventually they would come to cross. They're not parallel, and that requires Einstein to be right. I before E. That requires Einstein to be right, yeah? And that would mean that that would mean that space-time is curved, all right? Now, in order to do such a measurement, you need to have a clock. 1, 2, 3, 4, 5, 6, 10th, 100th, 1000th, 5, 6, 7, 8, 9. If your clock is only good to this digit, you can't tell. You need uncertainty beyond the nanosecond. So you need a clock with at least 2 more orders of magnitude, probably to be really confident. The error bars are too high here. And this can be difficult to do, but we live in the age of the atomic clock. And the atomic clock is good to what we call a femtosecond. So you can get atomic clocks where the uncertainty in time, I don't want to call it delta T again, where T is uncertain, I'll call it T uncertain, is approximately 10 to the minus 13th, which you'll notice is way out here. So you can get these clocks, and you actually find when you do the experiment that we find that delta T1 is not equal to delta T2. And in fact, you can use the discrepancy in Einstein, and Einstein's general relativity not only predicts the discrepancy, but very accurately predicts by how much the discrepancy will be given the height of the building. So what this means is that time, as we fundamentally understand it, right? You know, as we count time, a second, the length of a minute at, say, the top floor of the B building or the C building is not the same as a second on the bottom. And we define time, because this gets you into, well, what is time anyway? Is it a human construct? It is. It's a construct of counting. And it specifically counts light oscillations. And part of you might be saying, that's not really time. Well, everything you experience as time is due to an interaction of light and matter, right? Light and matter facilitates the atomic evolution of your cells. Your electrons are able to be excited and share orbitals with other electrons and other molecules because of interactions of light and matter. Cell division is critical for electrons have to change, do different things. So those are the connectors, interactions of light and matter. So you'll find that interactions of light and matter are fundamental to all known processes in the universe. And essentially, if you can't tell the difference between a state from one to the next, the time between it is meaningless. So, so time is just a certain number of, a second is defined as a certain number of oscillations of light. And when we define a second this way, which remains consistent with every other definition of time, we can see that it is relative and changes compared to one elevation to another. Okay? So use this discussion, and I'll put up other, like I said, some modified instructions so you just are a little clear on what I want you to do. Look at this recording again if you want to. And to write about learning about general relativity. Now, the reason we did all this is because we want to have context and get a deeper meaning behind black holes. Okay? Yes, within the 5 videos. There are actually 5 videos. Yeah, you don't want to explore much outside of those 5 videos because, as the host said, it gets really, really complicated really quickly. And if you're watching another video to help you out and it's like about metric tensors, the problem with general relativity is, one, it's not my specialty, so I'm not, I'm very much a student of it myself. 2, it's extremely complicated. And when I found when I started talking about general relativity, I would start with the mathematics and describe out there. I did take a course in it in grad school, but it was very, very math heavy, and it was not accessible to an audience. So then when I found myself explaining it at a level, it was very interesting, but it lacked the depth that I felt could be had. And then I found these series of videos, which is the sort of the perfect meeting ground for it. So I fear that most of the other things, you might find something that's good, but I find that everything else will be too basic and cut out too much of the meat that you could understand, and it'll just seem sort of ethereal and like this weird idea that isn't true, and too much, and it'll take math that requires an entire bachelor's degree in mathematics to understand. We're not talking like calculus 1 or calculus 2. We're talking, in order to understand tensor calculus, you need pretty much a whole math degree to really understand it. Yeah, I mean, if you really want to know what's going on with it, it uses a lot of the. It needs the sophistication of what we call analysis to understand going from different transformations and things like that. So you really do need the whole machinery of a mathematician. Yeah. Now, that being said, when you talk about physicists and mathematicians, I mean, in that level, we all sort of have that, but it gets that complicated that quickly. I was just thinking in my head all the courses that would be helpful for for tensor calculus, and you only need about half the math degree to do the tensor calculus, but to get the most out of it, I'd say everything helps. So yeah. Okay. 1, 2, 3, 4. No, I got 5. If you go up, the first one's at 351, then 414, 441, 501, and 517. And then we took our long break. And then Alina just posted the other one. Well, you know what I'll do when I do the instructions? I'll post the links again. How's that sound? That should fix it. Let me see this one. Yeah. Okay. All right, that should work. Okie dokie. So let's get back to our black holes so we understand what is going on there and why they really are pretty exciting. So again, our slides, good or bad as they may be, I'll just click till I get there. The sidebar is not helping very much. We saw a bunch of this stuff. We want to get to the black hole. So again, all your book says, all these books mostly say about space-time is that black holes are defined in terms of space-time. So we've spent a little time learning about general relativity so that there's more sense to these black holes, and that we are familiar and comfortable with the ideas that, one, we can't really picture space and time. This is a misleading picture, right? Two, the second one, is that time and distance aren't as fixed as we think they are, right? And we sort of talked about that a little bit in between, and that if someone's moving or in a different space-time than we are, we might not agree on, the person in that space-time and ourselves may not agree on how long a process takes or how long an object is, right? How big an object is. So we're going to find that these effects, we're going to talk about these effects, and that hopefully that will make understanding a little bit of the structure will make it make a little more sense. All right. So let's go on with our properties of black holes. So a black hole is an object whose gravity is so powerful that not even light can escape it. So the escape velocity of a black hole exceeds the speed of light. And the black holes are created, as far as we know, from some massive star supernova, and that can make a black hole if enough mass falls into the core. That is more than the neutron star limit. So basically, once we exceed the neutron star limit, we don't have physics that describes what would be inside there. But we observe that such objects exist. We call them black holes. And as one of you guys said earlier, the first composite picture of a black hole has been created. I'll try and find a picture of that and link it to you at the end of at the end of class. So black holes, some properties of black holes. Light would not be able to escape the Earth if you could shrink the entirety of the Earth to 1 centimeter. So in order for the Earth to be dense enough to be a black hole, the entire planet would have to be the size of a 1 centimeter mass. So that's about the size of a small marble. Okay. Now, the event horizon for large, so the event horizon is the, now wait a minute, did I skip something? I feel like I skipped something. Yeah, I skipped something. Okay. So, the surface of a black hole is the radius at which the escape velocity equals the speed of light. And that surface, that area, is called the event horizon. So basically, the event horizon is where the deformation of space-time is so great that light can't escape. And the radius of this horizon is known as the Schwarzschild radius. So the event horizon, we don't know what goes on inside the black hole, so we can't talk about the atomic structure of a black hole. As far as we know, a black hole packs all the mass of a star into an object the size of an atom, and because that density is so great, its curvature, the effects it has on space-time ripple out to the event horizon. And at the event horizon, one way to look at this is to say that the light can't escape. But to understand it from another perspective, once you are in a black hole past the event horizon, you are no longer causally connected to our universe. All right? That means that actions I take can no longer affect you, and vice versa. All right? Now, the event horizon of a black hole is about the same size as a neutron star, a little smaller. Okay, so it's about the size of a small city. However, the black hole itself can be thought to be atomic or subatomic in size. And again, we don't know what happens inside. And here's some more of these misleading pictures of space-time that are supposed to, you know, where these effects we're seeing that look spatially curved are really more temporally curved. And we'll talk about that in a minute. All right. So nothing can escape from the event horizon because we just talked about that. And no escapes means there's no more contact. This is where we're talking about causality. Now, one thing I want to talk about is there will be gravitational time dilation in a black hole, and what that and that's sort of explained here. And I'll talk about it a little. Okay, I'm getting confused. I'm going to go back to the chat room because I'm getting confused by my future slides. So we'll eventually talk about that in a little bit, but most people accept this sort of singularity definition. Beyond the neutron star limit, no known force can resist the crush of gravity. So that means quantum mechanics, in essence, turns off. The general theory of relativity itself predicts gravity crushes all the matter into a point known as a singularity. However, this can't be right because singularities imply infinities. And infinity is so much bigger than you can imagine that it's ridiculous. So think about this. Getting from here to infinity. Let's call this infinity. Now, what's the biggest number you can think of? Well, there's 10 to the 81 particles in the universe, right? But a finite number would be 10 to the 10 to the 81. And of course, we could do 10. We could raise this up 81 times to 10 to the 81, right? Where this arrow will indicate 81 raisings of 10 to the 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 81. All right? So let's compare that number to 1. If we look here with this representing 0 and this representing infinity, there's no discernible difference between that huge number we just talked about and 1. They are the same distance to infinity. Because this number, no matter how big it is completely and arbitrarily minuscule compared to infinity. Okay? You never get there. So to have a true singularity means a physical infinity. Most physicists and mathematicians are extremely skeptical of physical real infinities. There's still a few we can't explain away, or there aren't many we can't explain away. Still a few, but this is one of them. The other one is if you talk about the extent of the universe and the multiverse and things like that. Like, does it all end? Is it all finite? Is it all infinite? How big is it? How often does it repeat? There are fundamental questions where we haven't gotten rid of the infinities, but in a lot of our physical theories we have. So quantum physics disagrees, and we do not yet know what really happens inside a black hole. So quantum physics, basically this comes to general relativity being a continuous theory and quantum physics being a discrete theory. So quantum physics says there must be some lowest state for the black hole, that there must exist some lowest state. Quantum physics doesn't predict it yet, but all quantum theories have this feature, right? Where everything should still stack up like in a Pauli exclusion principle, but sort of in this new form of matter that we don't know or understand. So we do not yet know what happens, what really happens, and that is one of the big mysteries in all of physics, is what happens inside a black hole. And it's because those two theories don't agree with each other. So let's go. So what would it be like to visit a black hole? This is kind of the fun part, right? So if the sun shrank into a black hole, its gravity would be different only near the event horizon, right? So black holes don't suck. That is an important thing to note. They do not suck. So basically, if we had the sun, I'll make a short thing up here. Well, we'll talk about the futility of that particular exercise in a minute. So if we have our sun, if the sun disappears into a black hole, right? If you remember Kepler's law, the only thing that matters is the mass that we're circling around. If the sun became a black hole, that wouldn't change. It would only be near the event horizon, which, of course, not drawn to scale, would be extremely small. This little tiny dot, it would be even a smaller dot, but the space-time near the sun wouldn't change at all, or near the Earth wouldn't change at all, and we just orbit uninterrupted. So black holes don't suck things in. However, when stars are particularly dense, or if the black hole itself is massive and it's bigger, and over enough time, things will intersect with black holes, and they will be, become part of the black hole. The time scales for things to collapse into black holes is very long. Now, sending a probe to a black hole, also fairly difficult, if not impossibly difficult. So light waves take extra time to climb out of a deep hole in space-time, leading to a gravitational redshift. So what that means is that time will actually pass more slowly to the event horizon. So if you send a probe, if here's our black hole, right, and we send a probe, that means that as the probe approaches the black hole, it will take longer and longer and longer and longer to get to Gold won't matter. The black hole could be made of anything. The atomic structure very likely would break down. But if you send this in, the time itself takes longer for the light, the signal, to escape. So as you approach the black hole, it could take millions of years for the signal to billions to eventually the age of the universe. And that's before you get to the event horizon. So once you get to the event horizon, the probe becomes disconnected from the universe, and we get no information from it. No, it wouldn't matter whether it's gold or anything. Remember, time is oscillations. It absorbs things that cross its path, but the interactions are gravitational. So the existence of a black hole doesn't turn it into a sink, right? But with our sun, for instance, things will get heat up and be absorbed by the sun. You can certainly be absorbed by a black hole, but you have to actually cross its path. All right? So it's thought, for instance, early galaxies had a lot of matter that was being absorbed by black holes, creating what we call quasars. And as they ran out of material, as the density decreases near the black hole at the center of galaxies, which we're going to talk about in the next chapter, the quasars, the active galactic nuclei, become inactive. Okay, so black holes, if you fall past the event horizon, they certainly will not let you out. So in that sense, they suck. But remember, the event horizon is a teeny tiny little thing. You know, remember the radius of the sun is 100 times that of Earth. So you're talking about hundreds of thousands of kilometers, whereas the radius of the event horizon of a black hole is at most 2 or 3 kilometers. Like we're like 5 or 6 kilometers of a stellar black hole. They're larger for supermassive black holes, but because they're so large for supermassive black holes, some of the effects are actually more mild that we'll talk about. So there was an interesting episode of Doctor Who, though, where some interesting that I enjoy, where there was a giant spaceship in the shape of a cylinder. All right. And so there was one in this end, I believe the black hole was right here, and there was this was the control deck, and the population was mostly over here and broken out through a few parts of the ship. So the command deck recognized that 14 days had passed since the command deck came to the black hole. But on the other side of the ship, 1,000 years had passed. So the civilization woke up and colonized this part of the ship, right, using their terraforming technology, and it was actually one of the better episodes from the Stephen Moffat era, and interesting things happened. And the ship was about 5 miles long, I think. I could be making that wrong. It could be more. But you could have effects like this near a black hole, right, where time is going to pass much differently on one end of the ship to the other. Okay, and any probe we send, it would take longer and longer and longer to get closer and closer and closer. Okay. I don't know that a lie is the right word about everything you've been taught about black holes, but one of the reasons I wanted to go over space-time, again, was to give a lot of this stuff context and to make you realize how easy it is to not lie, but to get incorrect information. Okay? So again, it's hard to fall into the black hole. Tidal forces are pretty interesting because not only does time behave differently, but the mass of your legs here would be much longer than the mass on your arms. And this is called tidal shredding. So these forces would squeeze you and stretch you. And so the black hole is not friendly for life, right, when you get to this event horizon. However, the tidal forces would actually be gentler near a supermassive black hole because the radius is much bigger. So even though the mass is bigger for those black holes, the topology is more extreme for a smaller black hole, right? Because for a bigger radius, that topology looks more flat, right? If you have a big curve versus a little curve, the topology here is more compact, so you get the effects from each side are much closer together, even though they're overall more mild. Although here, for supermassive black hole, size can be close to like planet size and things like that. So there comes a point where the mass, where again, we don't know how big the side or what's going on with the inside of the black hole, but the edge of the black hole, right, gets the amount of space it takes up in, well, the distance, the more mass you have, the distance at which you can no longer recover causal information increases. Okay. So now, do black holes really exist? You bet they do, because in order to be a black hole, physically, all you have to do is be an object that is clearly smaller than a star with the mass of a star, and have a mass, that's greater than or equal to 3 solar masses, and not be a pulsar. And what I mean by that is not have light sources or things like that. And no one's seen a pulsar above 3 solar masses. So that tells you that light can't escape from the black hole. So we need to measure the mass, right? And we can use orbital properties of the companion stars. We can see these in binaries. And it's a black hole if it's not a star, right? So it's not luminous, and its mass exceeds the neutron star limit. And that's all you need to do to be a black hole. And there are tons of objects in the universe that fulfill that criteria. Okay? And we can see one here in Cygnus. You can see this is an artist's conception of what it looks like. This is the possible binary right there. So that should tell us what black holes are. And now we're going to see that black holes pop up, that the more we look, the more they pop up, and we see them in other places. So we can talk about black hole mergers, and it's thought that at the creation of a black hole during supernovas, these explosions called gamma ray bursts occur. So these are extreme events that can happen. So now, what causes gamma ray bursts? So it's thought that these supernovas or massive star death, dead star collisions will cause these to happen. So you can see the gamma ray burst in its outshines by quite a lot its host galaxy, right? And it fades over days. Now, days, what we call days, are extremely short periods in the cosmological scale, right? When we're talking billions of years. Gamma ray bursts will release more energy than a galaxy in a second. And keep in mind, galaxies have hundreds of billions, some of them trillions of stars. And keep in mind that a star, that the very lowest stars, right, the very least dim stars, will burn as much energy as humans would use in 100 years per second. All right? Our star, which is a bigger star, goes through 1 million years of human energy consumption per second, and the biggest stars would go through 1 trillion years of human energy consumption per second. Okay? So that's a lot of energy, all right, in those gamma ray bursts. Now, when we look at them, these were first detected in the 60s, and these are activities that, when they happen, actually, if we're in the path of one, can endanger life on Earth, and it is speculated that one of the 5 major extinctions may have been due to a gamma ray burst in our neck of the woods of the galaxy. And if they happen, there's nothing we can do about it. So observations in the 1990s showed that many gamma ray bursts were coming from very distant galaxies. So gamma ray bursts are not common today. They are more common in the early universe, and they're among the most powerful explosions in the universe. And the only explosion or incident that is more powerful than a gamma ray burst is the creation of the universe itself. Even the collision of galaxies, which we'll talk about, takes billions of years, which makes it spectacular and big, but very low power. Okay? Because the energies are enormous, but the time scales at which they happen are millions, if not 1 billion years, whereas the collision of a gamma ray burst happens in seconds. All right, so that means a lot more power. So could be the formation of black holes, could be the collision of neutron stars. It's one of those things that as soon as we can tie a gravitational wave event, remember measuring gravitational waves has only been doable, really, a direct measurement since 2015. So as we're able to tie gamma ray bursts to gravitational wave events, we'll probably get a much cleaner picture of the origin of gamma rays and understand what causes them. So when black holes merge, we can see here that they form these gravitational waves. And these gravitational waves propagate, and they represent waves in space-time itself. All right, and that curved stuff we talked about and spent the afternoon watching videos on. So when we look here, this was the gravitational LIGO signal, and we can see the merger of these two black holes produced a burst in gravitational waves. Now you have to do this in two. The only way the distances are so small for the atoms, the atoms in these detectors, that even talking in the building or a truck driving 20 miles away will affect the detector at that level. So the only way to really get a confirmed signal is to have two detectors about at least 1,000 miles apart, which is what we have here. We have Hanford and Livingston, two detectors. So you'll notice waves, and you'll notice they start to come in sync, and they're right in sync here during this part of the collision. And we can see here a merger of these gravitational waves coming from 1.3 billion light years away. And that's really spectacular, that collisions throughout the universe are affecting the space-time all around us today. And that's pretty crazy when you think about it. And so black hole mergers are the biggest forms of these. We have since measured a lot of these events. I believe we've seen neutron star collisions and some black hole mergers of various sizes. Gravitational waves are exciting because they're a new wave medium. The last new wave medium we had that was as fundamental to physics as gravitational waves were electromagnetic waves that we could measure in the early 19th century. When electromagnetic waves were first discovered, they were thought that some of the smartest people of the time were very insistent that they would be, there was no practical application to electromagnetic waves, but they were a scientific curiosity to study and understand. Boy, would their faces be green if they saw you on your cell phone, or us even having this meeting today, which requires the transport of information in electromagnetic waves. So it'll be an interesting future to see what we come up with to do with gravitational waves, because right now they remain very much in the realm of very fundamental science, but it'll be fascinating to see where that goes. Okay, so I think that is enough for today. And we will talk about we are going to expand our cosmic wheelhouse, if you will, to galaxies, our cosmic scale. So we will start our galactic discussion next week. I'll remind you all that on the 25th of May, so 2 weeks from today, is Memorial Day. So what I think, and then it says that the 26th, that the Tuesday is a Monday schedule. So I think what I'll do is, I'm still not sure whether I'm just going to record something over the weekend. Like, I might record something earlier that week and just put it up on the Monday or the Tuesday. I'm still not sure how I want to do that yet. So I will update you next week when I will know for sure. Okay? And I've taken attendance. So I'll put up the activity tonight. I'm going to work on that. I'm going to take a little break first, and then I'll put the activity up tonight. Let's have that due, say, May 29th. All right? No, they don't. So a gamma ray. So they don't worry about a lot of that stuff. Gamma rays. They do worry about cosmic ray interference. You kind of have to shield stuff from that. That's one of the hardest parts of sending these satellites up. But as far as asteroid collisions, space is just not very dense. So the chances of something like that colliding and killing it are very, 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 very low. So yeah, there's not too much chance of something being destroyed when you set it up there. Space is vast. It is very, very vast. I'm gonna stop recording.